So we're doing problems from chapter 9 today, and then we'll start chapter 10. Okay. So this problem says, one hazard of space travel is debris left by previous missions. Yeah. There are several thousand objects orbiting Earth that are large enough to be detected by radar, and the U.S. military detects them. There's something like well over 100,000 baseball size and bigger objects that are easy to detect by radar. But then there are much smaller objects. The problem is all these things are traveling fairly fast. Do you guys know what is the orbital speed, low Earth orbital speed? So it's 8 kilometers a second. So that's the speed at which the space shuttle or the International Space Station travels and all that kind of stuff. Okay, so even a tiny speck going at that speed, that can cause damage. You guys have had little rocks break your windshield on the highway? Okay, so that's the problem that you're dealing with. Except that those things are going at about 20 meters per second. This is 8 kilometers a second. Yeah. So there are several thousand objects orbiting the Earth that are large enough to be detected by radar. But there are a greater number of very small objects, such as flakes of paint. Calculate the force exerted by 0.1 milligram chip of paint, so a tiny chip of paint that strikes a spacecraft window at a relative speed of 4 kilometers per second, given the collision lasts 16 nanoseconds. Okay, so all right, so you learned in this chapter the force is change in momentum divided by change in time. Okay, so let's say what we'll do is we'll do a mild problem. We'll say this speck of paint hits the spacecraft and sticks to it. So the final momentum is 0. Okay, so we'll calculate the magnitude of the force, which is magnitude of change in momentum divided by the collision time. Okay, so that speck of paint got stopped in that amount of time. Okay? So final momentum minus initial momentum. So the magnitude of the force is, final momentum is 0. Okay. All right, so 0.1 milligram, 10 to the minus 3, milli is 10 to the minus 3, and then a gram is 10 to the minus 3 kgs. Okay, so velocity is 4 times 10 to the 3 meters per second. And this happens in 10 to the minus 8 seconds. Okay, so all these units will give you newtons. Okay, so the force is measured in newtons. So let's take your powers of 10. That's 10 minus 6, 10 minus 7, and that'll kill. So, and then you're left with 10 minus 1. So what you get is 4 divided by 6, 10 to the 4 newtons. So this is 0.67 into 10 to the 6,700 newtons. Okay. So what we are saying is, here's a speck of paint hitting that spacecraft window, exerting a force of 7,000 newtons. Do you have any idea of that force? Is that a large force? Okay, so your weight is about 600 newtons. So this is 10 of you or 11 of you. Okay, that's the force with which that speck of paint hits the window. Now here's the problem. So let's see, I've said this before. So if I push my finger against my palm with a force of 15 pounds, does this hurt? No. And the same force hurts. Okay, so this large force on a tiny area, okay, the pressure is enormous. So you, that can potentially cause damage. I don't know if this is what, you hear about leaks in the International Space Station and stuff like that. I don't know if they get hit by stuff like this. Yep. Anyway, yep.
Did you take the absolute value of the force it looked like? So you want this to be positive?
No, the direction didn't matter. I just wanted the magnitude of the force. All right. So, well, what this says is if the speck is coming like this and gets stopped, the force was in that direction. And we were just calculating the magnitude of the force. A 2,000 kg railway freight car coasts at 4.4 meters per second underneath the grain terminal, which dumps grain directly down into the freight car. If the speed of the loaded car must not go below 3 meters per second, what is the maximum mass of grain it can accept? Okay, so all right, so I guess in real life they have setups like this. So here's an empty car, grain gets dumped into it, and then it's going at 3 meters per second. And they have setups like this so they get large throughput, meaning so this grain will go to a ship or whatever. Okay, so they don't want this stopping, they want everything moving so they can load as much grain as possible per hour as possible. All right, so this guy, the empty mass is 2,000 kg, and we want to find the full mass. Okay. Now, when the grain is dumped in this direction, okay, the impact force is in this direction, and that doesn't change the momentum in that direction. So in the horizontal direction, the momentum is conserved. So initial momentum should equal the final momentum. Okay? So in the horizontal direction, initial momentum is equal to final momentum. So mass of the empty cart times velocity of the empty cart should be equal to mass of the full cart times velocity of the full cart. Yeah. So mass of the full cart is mass of the empty cart, velocity of empty cart. Yeah. So 4.4 meters per second divided by 3 meters per second. Okay, so the mass increased by 47%, okay, roughly 50%, roughly 1,000 kg. Okay, you can calculate that accurately. Okay, so that's how much grain you put, roughly 1,000 kg. Okay, so this says you're standing on a very slippery, icy surface and throw a 1 kg football horizontally at a speed of 6.7 meters per second. Okay. What is your velocity when you release the football? Assume your mass is that. Okay, so again, this is a conservation of, so you're holding on to a football and you're at rest on an icy surface. Okay, so initial momentum is 0, and then you throw the football, and so you have to recoil. Okay, so this is the velocity of the football, mass of the football. And so you want the final momentum to be 0 as well. Okay, so mass of person, velocity of person, plus mass of football, velocity of football. Okay. So velocity of person would be all right, so mass of football is 1 kg, 65 kg, and 6.7 meters per second. Okay, so if this velocity is positive, this velocity will be negative, and there's the negative sign. So it's 1/65th the velocity of the football. Okay. I'll write it like so. So it's just the mass ratio. The heavier the object you throw, the faster you'll recoil. Okay. All right, so a rocket is essentially you keep throwing footballs and you keep recoiling faster and faster. You keep increasing your speed. And here's a very interesting thing. Okay, so let's say you throw 10 footballs, one after another. So you're going faster and faster. But the total momentum of all those objects is what? 0. Okay. So similarly for a rocket in space, if you will. All right, in this problem, a projectile of mass 2 kgs is fired in air at an angle of 40 degrees. So here's a projectile that's launched at a speed of 50 meters per second at 40 meters per second. At the highest point in its flight, the projectile breaks into 3 parts. So 2 kg projectile breaks into these 3 parts. So what is the trajectory of the projectile? It's a parabola. At the highest point, what is the direction of its velocity? I'm sorry? Yeah, so it's horizontal. The velocity is horizontal. Okay? So its momentum is horizontal at the highest point. And then it breaks up into three parts. 1, 2, and 3. So right after breakup, what is the momentum?
It'll be the same as
Yep. So at the, I'm sorry? I'm sorry?
So total momentum before and after should be equal, right?
Right. Yeah. So at the highest point, P initial is P initial I. There's no Y component. And P final should also be, okay. So what I've written is it has no Y component. That's all. We are just emphasizing that fact. Okay. So the magnitude of the initial momentum should equal the magnitude of the final momentum and only X component. Okay, so they tell you, okay, so the three projectile breaks into three parts, 1 kg, 0.7 kg, and 0.3 kgs. The 1 kg part falls directly down. This is 1 kg. The 0.7 kg part moves in the forward direction, so 0.7 kg. And the 0.3 kg goes straight up. So okay. Now just before the collision, your momentum was in the x direction. So the final momentum has to be in the x direction. So this momentum should cancel this momentum. And this momentum should equal the initial momentum. Okay. All right, so before we do this, let's calculate the velocity at the highest point. Okay. So, well, so here is V naught. There's theta naught. So V naught is 50 cosine 40 I plus 50 sine 40 j. That's the initial velocity. Okay, there's the components, and this is equal to all right, so there's the x component of the velocity, there's the y component of the velocity, and at the very top of its trajectory, what happens? The y component goes to 0 because you have an acceleration. And at the very top, this is constant throughout the flight. So at the very top, velocity is 38.3 I plus 0j. Okay. And the momentum in the x direction is just mass times velocity in the x direction, which is 2 kgs times 38.3 meters per second equal to 76.6 kg meters per second. Okay. All right, so at the very top, so now you get this is 2 kgs. That breaks up into 3 pieces. 0.7 kgs, 1 kg, 0.3 kg. All right, so this has got a horizontal velocity. These two have vertical velocities. So the magnitude of this momentum should cancel the magnitude of this momentum, because here you have only x component of momentum. Okay. So since the magnitude will be equal, so 0.3 kgs times velocity of the 0.3 kg object should equal 0.7 kgs times velocity of the 7 kg object, or 0.3 kg object. Okay. And then they must give other information. The 1 kg part falls straight down after breakup of an initial speed with an initial speed of 10 meters per second. So they give us this 10 meters per second. Yeah. Oh, the 1 kg part falls straight down after breakup with an initial speed of 10 kg per second. That's 1 kg, and that is 10 meters per second. Okay, so the velocity of the 0.3 kgs is 33.3 meters per second. Okay, so this guy is going at 33 meters per second, this guy is going at 10 meters per second. And then it says the 0.7 kg part moves in the original forward direction, and the 3.3 kg guy goes straight up. So the speed of the 0.7 kg guy, this momentum needs to equal this momentum. Okay, so 2 kgs times his speed was 38.3 meters per second should equal 0.7 kgs times velocity of the 0.7 kg guy. And so the velocity of the 0.7 kg guy is 109.4 meters per second. Let's see if this makes sense. So this guy is going almost at 40 meters per second, and it breaks up into 3 pieces. And this guy, you see, is about 2.5 times, weighs 2.5 times less. So he needs to be going 2.5 times faster. 40 times 2.5 is roughly that. Okay. All right, so now we know the velocities of these guys: 10 meters per second, 33 meters per second, 110 meters per second. Find the speeds of the 3 pieces. How high from the breakup point does the 3-piece go before coming to rest? Where does the 0.7 kg piece land relative to where it was fired? Okay, so now we have found the speeds of these guys. That's part A. Part B, let's find how far up the 0.3 kg guy rises. He's going up at 33 meters per second. Okay. Now when you go straight up, like in lab you guys did last week, the height is V naught square divided by 2g. Okay, so that's how high he'll rise. Okay. 56.6 meters. This is roughly the height of the tallest building in the area on the beach. 56 meters is, well, 3/4 of a football field length. Okay. And then part C, what you want to find is where does the 0.7 kg piece land? So where does this fellow land? All right. So you fired a projectile. It went on a parabolic trajectory. And then what happened was at this point, the speed increased because of the explosion. And what is the trajectory of this guy?
Different parabola.
A different parabola, a bigger, a wider parabola. Okay. Okay, so we want to find these distances. So let's call this D1 and this D2. So the total distance traveled is D1 plus D2. Okay. Now, I won't prove this to you guys, but okay. What we'll do is we'll solve for the time it took for the projectile to go from here to there. And then what do you think will be the time for this guy to fall down? Same, okay? So this time of flight is the same as this time of flight, okay? So let's calculate that. Okay, and the way we'll calculate that is Vy equal to V naught y plus Ay times T1. At the top, the y component of the velocity is 0, and the initial y component of the velocity is there. Okay. And Ay, the acceleration is in the downward direction. It's negative 9.8 meters per second squared. T1. And so T1 so the shell gets to the top of its flight in 3.28 seconds. Okay. And the x distance it travels is just the x component of the velocity, the time of flight, and then the x d2 will be the x velocity times time of flight. Okay. Remember, x minus x naught is v naught xt plus 1/2 ax t squared. The acceleration in the x direction is 0. So d1 is the x component of the velocity was, for the first portion of the flight, was that. 38.3 meters per second times T1 was 3.28 seconds. Okay, so this distance is 125 meters. And now D2 is the velocity of the 7 kg piece, the 0.7 kg piece was 109 meters per second. So D2 is V naught x for the second piece times T2, which is 109.4 meters per second times 3.28 seconds. The time of flight was the same. Okay. Okay, so the total distance was D1 plus D2. Half a kilometers. So the shell would go from here to roughly Mainland High School. See, it was launched at launched at 50 meters per second. That's 120 miles an hour. Okay. And actually, it'll go up half a kilometer is almost up to, yeah, from here to Mainland High School. Okay. Okay, this is a similar problem. Do you want me to solve? I'll solve it. There are 3 deer standing on a rock. So the initial momentum is 0. And then a gunshot goes off and they scatter. So the final momentum has to be 0. And you're finding one of the velocities. Do you want to see that? Okay. All right, so 370 kg deer are standing on a flat 200 kg rock. So they all have the same mass. That is on an ice-covered pond. A gunshot goes off and the deer, this is, that's deer. Okay, deer scatter. With deer A running at that speed, deer B running at that speed. So, of course, they're all horizontal speeds. Okay. And deer C running at that speed. What is the velocity of the rock? Okay. So here are the 3 deer standing, and initial momentum is 0. And the rock goes this way. The deer, these are all So the final momentum has to be 0. Okay? The final momentum is mass of the rock, velocity of the rock, plus mass of the deer times velocity. All the deer masses are the same. Velocity of the rock A, velocity of rock B, plus velocity of rock C. See, this is the momentum of deer A, deer B, deer C. Okay. So this is 0. Right. So really this is the 0 vector. We'll bring this to the left, and so the velocity of the rock is negative mass of deer over mass of rock okay. Mass of deer is 70 kgs and the mass of the rock is 200 kgs. So it's minus 70 divided by 200. And then the sum of these velocities. Okay, so let's add up all the velocities. So this is 3 plus 1.2, 4.2 I, and then 13, so minus 5j. Okay. Yep.
Why isn't it 3 times 7? Because there's 3 7.
Yeah. So this is the momentum of deer A. This is the momentum of deer B. This is the momentum of deer C. And
Got it.
okay, so that's the velocity of the rock. Okay. Again, momentum conservation problem here. The initial momentum, and so the final momentum after the scatter should be 0. Okay. Okay, this problem says a cube of side A is cut into another cube. So you cut this cube and throw it away, as shown in the figure. Find the location of the center of mass of the structure. Okay, so when the whole thing was there, when this was full as well, the center of mass would be at the geometric center, which would be, so here's the x-axis, which would be b by 2, b by 2, b by 2. Okay. So the center of mass for the whole cube, would be b over 2, b over 2, b over 2. All right. Now that you cut away this piece, where do you think the center of mass of this guy would be? So let's say for the whole cube it was over here. Where would be the center of mass for this piece? Which way would it move?
Like in opposite direction.
Yeah, it would move away, so it'll be somewhere there. Okay? And that's what we want to find. Find the location of the center of mass of this structure. Okay? All right, so here's what we'll do. So imagine the whole piece there. So fill this up. The center of mass of this guy is A by 2, A by 2, and A by 2. Let's call this M1, and we'll call this M2. And we don't know its center of mass, and that's what we're trying to find. Okay? The center of mass of the combined object we know is that. Okay? So let's call this mass M2, and this mass is M1. Let me write this. Okay, so imagine the whole thing. Okay? So we're trying to find the center of mass of M2. Okay? All right, if you look up your formula, so X center of mass is the mass of Mi Xi. What this formula says is Mi is mass of each piece, and that's the coordinate of the X coordinate of the center of mass of that piece divided by the total mass. Okay? Okay, so you're imagining the whole piece. Okay. And the X center of mass of the whole piece is B by 2. Yeah, so B by 2 is equal to M1 A by 2 plus M2 X center of mass, which we don't know. Okay? Or we'll call it X2. Yeah, we'll call this X2. That's a better notation. So X2 divided by total mass. So we'll call the total mass M. Okay, so you have to understand that. Okay, what we're trying to find is X2. Okay. Now, before we do that, let's find M1 and M2. What is M1? M1 would be the mass of this guy. If the total mass is M, the mass of M1 is the fractional volume. Okay? So M1 would be A cubed divided by B cubed times M. And what would M2 be? What would M2 be? What is the volume of M2, of the second piece? You throw away that piece. Okay? Okay, so that's the mass M2. All right, now that we have that, let's solve for X2. So M times B by 2 equal to A by 2 M1 plus M2 X2. Okay, so X2 is M by 2 B minus M1 by 2A divided by 1 over M2. Okay, just a whole bunch of algebra. All right, so let's write this down. Okay, X. All right, so now let's substitute this. So m2 is b cubed minus a cubed over b cubed times m, b by 2 m minus a by 2 a cubed by b cubed m. That's a good thing. The center of mass should just depend on these dimensions. Okay. All right, so this is b cubed divided by b cubed minus a cubed. And the half is a common factor. Half comes out. Times, this is b to the power 4 minus a to the power 4. Okay. This b cube cancels. So this is equal to 1/2 b to the power 4 minus a to the power 4. Okay, so what we'll do is we'll try and so what we had started off by saying was, for the whole piece, that's where the center of mass was, and when you cut out this piece, it would move away diagonally like that, along that diagonal. So let's show that. So from b by 2, it's going to move away in that direction. Okay? So this is just for the x coordinate. Okay, so but let's. So 1/2. I'll pull out b4 at the top. 1 minus a to the power 4, b to the power 4. Do the same thing in the denominator, b cubed. 1 minus a cubed, b cubed. So this is equal to b by 2. 1 minus a4 b4, 1 minus a cubed b cubed. So this is x2. What is y2 and z2? Same, very good. So x2 equal to y2 equal to z2 equal to b by 2, 1 minus a4 b4. All right, now let's look at this beast. What do you want this to be? You want this to be, if you want the center of mass to move to the right, you want that number to be greater than 1. Okay? What is a by b? Is it less than 1 or 1 greater than 1? A by b is less than 1. Okay? So, since it's less than 1, this number is smaller than this number. 0.5 times 0.5 is 0.25. Okay, if you take a number less than 1 and raise it to a integer power, okay, so this number is less than this number, so this number is bigger than this number, so this number is bigger than 1. Okay, and so as expected, the center of mass of that piece, the center of mass of this piece is diagonally further away. Okay, and this has the right limit. So if a goes to 0, where should that center of mass be? I'm sorry? B over 2. If A goes to 0, this is 0, this is 0, it would be at B over 2. All right. We'll do one more center of mass problem. This says find the center of mass of a thin wire of mass m and length L bent in a semicircular shape. Let the origin be at the center of the semicircle and have the wire arc from plus axis across into there. Okay, so okay. Okay, so you want to find the center of mass of this object. Obviously, the center, the x coordinate will be there. So from symmetry, it'll be there. The y coordinate will be somewhere there. Okay, and so we really are finding y center of mass. Okay, so yeah, the x coordinate. Yeah. Now, where is the center of mass if the circle were full? Right in the middle. Okay. So the center of mass of this guy will be there. The center of mass of this guy will be right symmetrically opposite, and and so on. So this is what we want to find. Okay. Now, so this is a continuous distribution. We have to set up an integral. Okay. And if you look at your notes, the y coordinate of the center of mass is the total mass of the object. We'll call the m the total mass of the object times y, the following integral, y dm. Okay, what this means is, let's say, so when you're setting up an integral, what we'll do is we'll break this guy up into little pieces. That's the mass of this little piece, and this is the y coordinate of that piece. Okay. So you take the y coordinate of that little piece, there's the mass of that little piece, sum over all the pieces, summing is integral, divide by the total mass of that piece, and that gives you the y coordinate, the center of mass coordinate of that object. Okay. So that's what that integral is telling me. That's what that equation is telling me. Now, what is the problem? You have to evaluate that integral. That's the problem. Okay. All right, so let's set up an integral. So let's say this is, let's say that is d theta. Okay. What is the total angle that this object subtends? Pi. Okay. So dm is d theta divided by pi. That's the fractional angle times the mass. Okay. And then what is the y coordinate? So let's say, this angle is theta. Okay. So sine theta is y over r. So y is r sine theta. All right, so let's, y center of mass is 1 over m. Y is r sine theta. And dm is d theta m over pi. The m cancels, okay? And so this is r over pi sine theta d theta. And what are the limits of integration? What does theta change from? 0 to pi. Theta goes from 0 to pi. And integral of sine theta is minus cosine theta. Cosine of pi is minus 1, minus of minus 1 is, or so plus 1. And then cosine of 0 is 1, but this is minus, so minus 1 is plus 1. So two over pi times r. So y center of mass is 2 over pi r. Let's see if this makes sense. Well, you know that the center of mass has to be somewhere there. It has to be less than r. It can't be there. It has to be less than r. And this is less than 1. So it is less than r. Okay. And in the limit r going to 0, so here's another limit. In the limit r going to 0, what happens to y center of mass? As you make the arc smaller and smaller, that's what
It also goes to 0?
it goes to the origin. Then it becomes a point particle at the origin. Okay. And it has the right limit. All right, let's do a couple of rocket problems and then we'll take a break. Okay. A rocket takes off from Earth and reaches a speed of 100 meters per second in 10 seconds. If the exhaust speed is 1500 meters per second and the mass of the fuel burnt is 100 kg, what is the initial mass of the rocket? Okay. So mass of the fuel is 100 kg. Okay. Okay, so this takes off from Earth. Okay, so you guys can look up this expression. It's exhaust velocity log m initial m final minus g t final minus t initial. Okay, what this formula says is if you take off from the surface of the Earth, your final velocity of the rocket minus initial velocity is the exhaust velocity natural log of initial mass of the rocket minus final divided by final mass. So initial mass is final mass plus the fuel, g times that. Okay, so the final velocity is 100 meters per second minus 0, 1500 meters per second log. So initial mass was the final mass of the rocket plus 100 kgs. That's how much fuel you burnt, minus 9.8 times. I haven't written down any units, but they're all in SI units. Okay. So this would be 100 equal to 1500 log, well, I'll just write it back as that, minus 98. Okay, so 198 So e to the power of that is that. So e to the power of 0.132 is mass initial over mass final. Okay, so m final, you subtract that, you're left with 0.14. M final would be 100 divided by 0.14. And so the initial mass of the rocket is the final mass plus 100 kg of fuel burned, which is 809 kg. Okay. So this is a similar problem. So they say how much fuel would be needed for a 1,000 kg rocket. That is the mass of the rocket with no fuel. So that would be the final mass. To take off from Earth and reach 1,000 meters per second in 30 seconds. The exhaust speed is 1,000 meters per second. Okay, so V final minus V initial. Okay, so the final speed is 1,000 meters per second. Exhaust speed is 1,000 meters per second. Log m initial over 1,000 minus 9.8 into 30. Okay, so we'll bring this over there. That's 1,294. And divide, so 1.294 equal to log mi over 1,000. That's base e, so e to the power of that. So the initial mass of the rocket is 3,600 kgs. All right, that finishes the